another code here. Let me just run it. Do you see that this code has a bunch of numbers here? Yes. Okay. Bunch of numbers. You run this code. Sorry, that gave away the surprise, but you get a fern. It's called Barnsley's fern, and this is formed also with these lifeless formulas, some numbers and whatnot. Okay, so what's going on here? You remember the Gauss game? What it was is a linear transformation. You took a bunch of points, you transform it into a certain point, right? This is also a linear transformation, and that transformation is governed by these numbers. So you get, like, imagine a vector, okay? Then you multiply that vector with a matrix. It takes that vector to some place, right? It transforms it. So this is the matrix. This is the additional vector to translate it. So you basically squeeze it or stretch it. I mean, you have a square. Okay, let me show you. Let me show you the next code. It's the same code. You just have the steps. So you start with a block of square. Okay. As you remember, there were four matrices at the top, like these 4 matrices. Okay. So one of them takes all these points and maps it to this stem, okay? Just maps it like this, okay? Another transformation takes all these points and maps it into this shape, okay? Linear transformation, right? It rotates, squeezes, tilts, and just puts there. This is another transformation, right? But then you take these points and map them to there. I hope I'm making sense. Am I? Then you take these points and make the transform, etc., until you get this fern. Okay, we did it 4 times. Let's do it 10 times. Square, then this thing, then that thing, then that thing, then this one. Gets closer and closer to the fern as you keep doing this mapping. Okay. I hope you are happy. Yes? Does this count as something natural? Sort of. Well, let's talk about something else. Let's talk about L systems. Let me show you the Wikipedia page for L systems. Okay. Yeah. Or Linden-Meyer systems. It's called parallel rewriting system. I have an example so you will understand hopefully what parallel rewriting means. But basically you start with simple thing and you make a transformation. There is a good example here. Let's say you start with an axiom and there are rules. If you have A goes to AB. If you have B goes to A. So you start with A, then A becomes AB because A goes to AB, but then A becomes AB and B becomes A. Did you follow that? So what is the connecting theme here? The Mandelbrot set, Julia set, L systems, fractals, everything, self-reference. Okay? Yeah. Okay. So I happen to have a code here. What does it do? if you have A, basically A becomes B minus A minus B. Okay, let me just, I'm shortening it out for you. A becomes B minus A minus B, and B becomes A plus B plus A. So let's do it in the notebook. If I start with A, goes to, what was it? B minus A minus B, right? But what was B? A plus B plus A, and then there is a minus. What was A? B minus A minus B. What was B? So I do have a minus here. A plus B plus A. So what, right? So what? Well, here's what we are going to do. A will correspond to move forward. Forward. B will also correspond to move forward. Okay. Plus will correspond to turn 60 degrees right, and minus will correspond to turn 6 degrees left. Okay. So let's start with go forward, turn 60 degrees right, but don't go forward yet, right? It's just you were going this way, turn 60 degrees, right? We are here. Did you follow it? So I start from here. I do A, so I move forward. I go here, but I'm pointing this way. It says turn 60 degrees right, so I point this way and move forward, turn 60 degrees right and move forward, etc. I have a code for it, so no worries. This code is doing that. So let's do it for 3 steps. This is what it is generating, okay? Let's do it for 4 steps. This is what it is generating. Do you see where it's going? Let's do it for 7.7 thing. Yeah, right.
Can we also make a specific curve with something like that?
Yeah. So you get a Sierpinski triangle all over again. That all fragrance from once upon a time, right? Very good. Very, very good. So all these are connected, related. Okay, what's next? Am I done with this? I think I'm almost done. So after this point, it's blah, blah, blah. Okay? I will just talk. So what I want to talk about, for example, I want to talk about formal grammar. I mean, basically, Noam Chomsky figured out the origins of our language, right? Like, if you remove all this Frenchness, Englishness, Germanness, whatever, what remains? And what remains is this graph rewriting structure. Like, you start, I'm going to say something that is a thought, okay? But that thought is formed of these nouns and pronouns and whatnot. Now let me show you the paper by Chomsky. It's this kind of process, like sentence. I don't know what these mean. Maybe you do. Do you? But what? What is this? Noun? So you do know what it is. But you understand that. Do you sense the connection here? You start with an axiom, you rewrite that thing, and so basically somehow these things hold a key to the consciousness. Okay, what makes you your illusion of I it can be described at some point with this kind of stuff. Speaking of illusions, self-reference, we have to mention Douglas Hofstadter. Okay?
By the way, can I ask a question? Do these need to be deterministic? Or
No, it can be probabilistic. Right? This is how ChatGPT works, doesn't it? Isn't it?
I don't know.
Because there's this recurrent structures there, and it just tries to find what is the next word. Right? They turn the words into tokens, like numbers, and it has some internal structure that you put in the previous numbers, and it tries to guess what is the next number, and that number corresponds to a word. What?
I think the normal verbs is the sound and we create a formalized and create a sentence. But ChatGPT, I think I'm in the AI, I don't know, there is a formalized thing and we use it and create it. So kind of.
There is a what?
There is a formalized the language and use it to.
Do you think that ChatGPT is just copying the previous answers? Yes. Yeah, because what I'm speaking right now is, I agree that it's vague. I just throw out some ideas at you, okay? So there is some branching going on, there is some self-reference going on. We have to mention Douglas Hofstadter at this point. So, physics. Okay. Let's start with Hofstadter's butterfly. Okay. Hofstadter's butterfly is actually a graph that connects the first part of this course to the second part of this course. Because I happen to have it here. I had it somewhere here. This is from Hofstadter's book. So this is Hofstadter's butterfly. What is it? Surprise, surprise. This side is energy, and this is magnetic field. Okay? Do you remember those electrons, tight binding stuff in 1D chain, etc.? Let's put it in a square lattice, okay? And then apply magnetic field and do a bunch of calculations, okay? What you get, do you remember the bands? There were bands, there were solutions to the problem, Schrödinger's equation, etc. So this plot is basically telling you that if you have this magnetic field, which is a reduced magnetic field, it's a ratio of magnetic fields, you know this synchrotron radius? When you have electron inside magnetic field, it rotates. So magnetic field introduces some length to the electron, and the lattice have some length. When these lengths are in harmony, like when they are, it's 1/2, for example, okay, this is 0.5, 1/2, you get two bands. They are actually kissing here. There are actually two bands and they are connected. When you are at 1/3, you have 3 bands. Sorry, this is not 1/3. This is 1/3. So you have 1, 2, 3 bands. Do you see it now?
Yeah.
Where is 1/5? It's here. So you have this 1, 2, 3, 4, 5. Okay? If it's if it's irrational, what does irrational mean? It means that you cannot write it as P over Q. Okay? In other words, Q goes to infinity. Can you guess what you get there? I mean, if you think about it for 1 day or 1 month, you might guess, because the answer is within these lectures. Let me give you the answer. You get a Cantor set. Okay? Because Cantor set has infinitely many points, and you happen to have a Cantor set here. Okay. How about fractality, right? Self-similarity. Hofstadter realized that basically you have this, you start with this thing, and you basically take this image, this whole thing. Let me actually do this. Let me first draw this. Okay. Yeah. Okay. Okay. It will not work. Okay. Wait a moment. Okay. So you take this image. Then let's say you copy this image and you put it here. A copy of this image. Okay? So you take the whole image, you put it a copy inside. Let me show you that this is indeed the case. Do you see these wings of the butterfly here? Like this. Now, let's distort it and put it here. Do you see the wings again? They are here. Yes? So I really, 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 really recommend you to watch this video on YouTube. Where is it? I think it's this one. The human story lurking behind the Hofstadter's butterfly. And this is Hofstadter, by the way. And it's a very nice video. Me and Hofstadter has, I mean, I don't want to elevate myself or anything, but we have so many things in common. His academic grandfather is my academic grandfather's grandfather. So we are not that far away. He's talking about his struggles in getting PhD. Although he's, okay, now the comparison stops, okay? He is a genius, this guy, and his father is Nobel Prize laureate. That's why you have this Leonard Hofstadter in Big Bang Theory, because of his father. Okay? Robert, I think. Anyways, there are a bunch of things in his life, and he's trying to get this PhD in, he enjoys it. He enjoys it a lot. But his heart is somewhere else. He's trying to write a book. Okay, he's not trying to write a book. He's trying to not write that book, actually. He's so full of ideas that at some point he puts it in a drawer, and if he opens that drawer to write the book, he punishes himself so that he stops doing what he likes and gets his PhD. His book is then later on his book wins Pulitzer Prize. His book is called Gödel, Escher, Bach. Have you heard of that book?
Yes.
Yes, very good. So these are three people: Gödel, Escher, and Bach. Bach is Johann Sebastian Bach, the composer. Escher is this guy. This guy who, you get the idea why he is in the book, right? Immediately. It's all about paradoxes and self-reference, whatever. I mean, there you go. Like self-reference. It's just symbol of self-reference, right? Who is left? Gödel, right? Do you know Gödel? Kurt Gödel.
His incompleteness theorem.
Yes. Gödel's incompleteness theorem. As I promised, I'm just talking, right? So there is this thing called Principia Mathematica. It's a book, okay? And the aim of this book is to start from the very basic axioms and just use this rewriting, like just pure logic, and go to all the places possible in mathematics. Like, do you know when they reach 1 plus 1? Page 379. Like after 370 pages, they reach at a proposition which is 1 plus 1 equals to 2. Okay? It's that deep. And before they start with this book, they had to make sure that they get rid of paradoxes in set theory. Okay? It's based on set theory. And set theory has these paradoxes right at the beginning, like it's related with something like sets that have all the sets, sets that don't have all the sets, etc. Like this statement is false, kind of paradoxes. So they get rid of that paradox, and they hope that they will start from the nuclear axioms, and they will create all mathematics. And hopefully what is generated is complete, meaning that every truth can be found by starting from there. So everything has a proof, it's complete, and it's consistent. You will not get an inconsistency at some point. Are you with me?
Yes.
Yes? Well, they write like 3 large books and they get tired, I guess. But at some point, Gödel uses Principia Mathematica's principles and he proves that there are true statements that can't be proven. Hence, mathematics is incomplete. If you were thinking that any theorem in mathematics that seems to be true can be proved, it's not the case. Okay? So people are now, we don't know which one is that one. Okay? We don't know which theorem can't be proven. So let's say the most famous one is Riemann's hypothesis, right? Some people, when they are tired, they say that maybe it's just one of those statements that can't be proven, when maybe it's outside that. And even if let's say you can't prove something and you just patch it, you make it an axiom. Okay? Gödel doesn't give you any chance. Like he proved that if you put it as an axiom, then there will be definitely something else that can't be proven. Okay? There's no escape from this. All right.
Also, there is something even stronger about that.
Yeah.
It says that for any system prove its own consistency must be inconsistent. So
Oh yeah.
So we can't know if our axioms, Zermelo-Fraenkel choice, are consistent, whether do they cause contradictions or not. And if we know, then it must definitely be false.
Do you understand it? There's a nice video. Maybe we'll watch it. We still have 20 minutes, and let me think if I made all my points. I talked about Hofstadter. So in his book, he keeps talking about, like, he likes these riddles, puzzles with paradoxes. Here is a paradox. Okay. Give me the number that can be described. Okay, let me think about it. What is the smallest number that needs 30 words to be described? Do you understand the proposition?
Yes.
So let's say 1 is 1, 2 is the one that comes after 1, etc. Right? And we are searching for the smallest number that can be described by 30 words, right? Do you see the paradox already?
Yes, because if such number exists, then we can say, oh, it's the first number that requires more than 30 words to describe,
and
it's less than 30 words.
And that description is less than 30 words. Do you understand it? Amna? Yes? It's this kind of taking something and putting it back inside that creates this lifelike problems. Somehow, suddenly, something that is lifeless, like ones and zeros, complex numbers, when you have self-reference, it stands up and starts walking. Okay? So, it's a long book of puns, all kinds of trickeries, juggling with words. Okay. Let's. Where is Hofstadter? Here is Hofstadter. Here is Gödel, Escher, Bach. Neurons, colony of ants, like there is this magnific crab that corresponds to Bach's Magnificat. Like that's kind of like one dialogue contains a story about genie from the Arabic jinn and various tonics of both the liquid and musical varieties. Look.
Gin tonic.
Yeah, but there is a liquid tonic, gin tonic, but there's also in music there's dominant and tonic, you know. So, do you know crab canon, for example? Have you heard of it? It's like it's composed of. So in Bach's time, there were these musical puzzles. Okay, he just. Okay, I don't have a nice picture here. Maybe. Okay, let's watch this one. No, this is not a video. Anyways, I mean, he figures out some notes, okay, but underneath, the same notes are played backwards. And he makes sure that they sound together nice, okay? It's this kinds of music, mathematics, self-reference. And what is the point? What is the point? He gets so involved with these puzzles and puns that apparently he couldn't transfer his message. And his message is that he writes another book to convey that message. And that book is called I Am a Strange Loop. He wants to call it first I is a strange loop, meaning that the idea of I that you have is coming out of a strange loop that you generate in your mind because you have these re-entrant connections between neurons. So you have this thing swirling inside and you have this loop, and that loop is what gives you the idea of I. Okay? Good. Let's watch a video.